So let's take a look here. I will do this, it's a two-step problem. We have a spring. When you don't hang anything on it, the spring is just sitting there. That's the natural position. Now you attach a mass to it and you lower the mass slowly, and the spring sags and the mass is here. The speed of the mass is 0, and so it's not moving. And the question is, find the force constant of the spring. What is K, the spring constant? The mass is not moving, so there are two forces on it. So the net force on it is 0. There is the force of gravity this way, and it's mg. I'm talking about the force on this mass. And then there is the force of the spring upward, because you stretch the spring will try to go back to its natural position. So that's the force of the spring. And the force of the spring will be, if this is down, the force of the spring is up, so it's just K times Y, right? And it's in the upward direction. And here Y is really like -3.5 because it's sagged. But I'm just using magnitude. The direction I can determine always. So I conclude that the net force is equal to 0. That means the force upward and the force downward, they have to be equal to each other. And therefore Ky will equal to mg. And therefore K will be mg divided by y. And let's calculate this force constant of the spring. So we get the mass attached is 0.5 kilograms times gravity, 9.8, and then divided by y, which is 3.5 centimeters, that's 0.035 meters. So I get a force constant of 140 newtons per meter. So that's the force constant of this spring. Remember, it's a constant, so it's a property of the spring. And so when you have a spring and you have the force constant of it, that's it. That's a constant, and it's not going to change, ideally, for that spring. So let's go to the next problem. We're going to use the same spring, but now I'm going to orient my spring horizontally. Here's my spring oriented horizontally, and the force constant of this spring is 140 newtons per meter. Okay? I have a mass, and the mass is 0.5 kilograms. 0.5 kilograms. It's coming in with some initial speed. It hits the spring starts to compress. It compresses and compresses until it gets to the mass, it gets to this position here. It compresses by 2.7 centimeters, and the mass comes to rest. The question is, what is the initial speed of the mass? Now, my system here is the mass plus spring, right? Mass plus spring. The interaction between them is the spring force, and so there is potential energy associated with that, and that is equal to 1/2 kx squared. Are there any non-conservative forces involved here doing work? And the answer is no. The wall's force on the spring is not doing any work. Gravity is downward, and so it's not doing any work. We're oriented this way. The normal force is not doing any work. So we only have the spring and the mass interacting with each other, and so we have the total energy is conserved. So I will say, here I'm using 0 for initial and F for final. So I would say the total energy at the beginning should equal to the total energy at the end. Total energy at the beginning consists of kinetic energy at the beginning plus the potential energy at the beginning. And notice here, when I say potential energy, I'm talking about spring potential energy or elastic potential energy. If we had gravity, we would have another potential energy on top of this spring potential energy. We will in a moment. You just have to add it, that's all. And then here I have the equals the kinetic energy at the end plus the potential energy at the end. Just back this chart. The kinetic energy at the beginning is 1/2 mv at the beginning squared. The potential energy in a spring is 1/2 kx squared, 1/2 kx initial squared. And then the potential energy at the end, I should put an equal sign, is 1/2 k v at the end squared plus 1/2 kx at the end squared. Now, let's look at what all this means. When the spring, what we mean by x is how far did we compress it or stretch it. At the beginning, the spring is neither stretched nor compressed. Therefore, this x at the beginning is 0. It's neither stretched nor compressed. So this one is 0. The speed at the end, the mass comes to rest, so this part is 0. So here's what happens. At the beginning, we only have kinetic energy in the mass. There is no potential energy stored in the spring. The mass hits the spring compresses, the mass comes to rest, so the kinetic energy of the mass is lost to potential energy in the spring, is not lost, stored as potential energy in the spring, and when the mass rebounds, it will come back, that kinetic energy comes back. So we end up with this, the kinetic energy at the beginning of the mass at the beginning will equal to the potential energy stored in the spring at the end. You can multiply both sides by 2. We want the speed at the beginning, so we will divide by m and then take the square root. So you get v initial will be k over m. You have to take the square root. But when you take the square root of x final squared, you just get x. And we get here the square root of k over m. Technically, when you take the square root of x squared, it's the absolute value, but I would just plug in the magnitude. So k over m, k is 140, the mass is 0.5, and x is by how far did the spring compress, and it's 2.7 centimeters, that's 0.027 meters. And so we get v at the beginning is equal to, we need our calculator here, 140 over 0.5, take the square root of that, and then multiply by 0.027, that gives 0.45, 0.45 meters per second. Okay. Next problem, we're going to combine. Imagine you have a spring this way, like that, and the mass falls on it. So now you have gravitational plus spring potential energy, right? Because gravity will be doing work. So our system will include the mass, the spring, and the earth. And that will give us kinetic energy in the mass plus potential energy stored in gravitational potential energy plus spring potential energy or elastic potential energy. So let's take a look at that problem. So sorry, I thought we will do the vertical spring, and that will be later. Come back to it, probably in the problems also. So let's do this pendulum thing. So you have a mass attached to a spring, and it swings. So at the highest point here, the speed is 0, and you let go, it swings. And the question is, as it swings and gets to the lowest point here, what would the speed be? So as it swings here, let's call here v initial. It starts at 0, so v here at the bottom, let's call it v final. What would it be? What would it be? Okay, what would that be? Well, we can draw we have to define our y-axis here, right? So let me do it a little more. So here's that, and like this, and here is my y. This is y final. I would call that the 0, and this is y initial. I have to figure what that is. I have to figure what y initial is. Okay, what y initial will be. Actually, I take it back. It's probably easier to do it this way. I'm going to define y equal to 0 here. y equal to 0 is there. So what is this here? So what would y initial here be? And what would y final be? When the mass comes all the way here, y final is the whole length, but it's below. Y0 is here, that's the positive, and this is the negative. So it will be negative L, negative the length of the string. Right? So if it's just hanging, if this is 0, from here to here it's L, but it's I'm defining this is the positive y, and so this will be negative L, if you like. We could also define the positive to be downward, but that's unusual. So I would just stick with upward to be positive. So what would this be? Well, this will be from here to here, it's the adjacent to theta, so it would be L times the cosine of theta. So it would be L times the cosine of theta. So think of this triangle here. So this is L cosine theta, but it's below, so I have a minus. Sign there. All right, so now what's our system and how do we go from here? Our system will consist of the mass in the earth. The mass in the earth. So there is an external force on this system doing work, and that force is the force of tension, but the tension will do 0 work. Because think of it, as the object moves, it moves along this arc, and the tension is always perpendicular to that arc, and so it's doing 0 work. So we say the total energy at the beginning, at the total energy at the end will equal to the total energy at the beginning. Total energy at the beginning consists of the kinetic energy at the, total energy at the end consists of kinetic at the end plus potential at the end. And then the energy at the beginning consists of kinetic at the beginning plus potential energy at the beginning. Kinetic energy at the beginning, at the end is 1/2 mv final squared. Potential energy at the end is mgy final. This is gravitational potential energy. Kinetic energy at the beginning is 1/2 mv initial squared. And potential energy at the beginning is mgy initial. We're assuming the initial speed at the beginning is 0, so this whole part drops, becomes 0. Notice the mass can be divided out. And I want V final. So I have, let me do it this way, so I have 1/2 of V final squared is equal to, move this to the other side, and then factor the G. So you have G, Y initial, minus Y final, like so. And then multiply both sides by 2. So you get V final squared is equal to 2G, and then Y initial minus Y final. Let's substitute. Y initial minus Y final. Y initial is negative L cosine theta. Negative L cosine theta. And Y final is negative L. So you would have V final squared will equal to 2G times minus becomes plus, so this is positive L, so it becomes negative L cosine theta plus L. So that is L minus L cosine of theta. And I'm going to simplify it one more time. I would factor the L out, so I get V final squared, or V final will be the square root of 2G L times 1 minus the cosine of theta. And now we will plug in the numbers. We get 2, G is 9.8, L is 0.78, and then square root, and then 1 minus the cosine of 60 degrees. And so you get V final. Let's get my calculator here. So you have V final will be 2 times 9.8 times 0.78, and then cosine theta is 1/2. Cosine of 60 is 1/2, So 1 minus a half is a half, so multiply by a half. And then you have to take the square root. So I get 2.76. And let me make sure I get the right number. Yeah, about 2.76, 2.8. So I get 2.76 meters per second. So that is this one. So I would like to just now look at the potential energy stored in a spring. We said if you have a mass attached to a spring, then the potential energy stored in the spring is 1/2 kx squared. The force is minus kx. So let's use this. Let me try to draw this. The potential energy as a function of x. So here is x, here is u, so here is x. How does it look like? How would you plot 1/2 kx squared? Oh, it's a parabola, it's concave up. It looks like this. Okay. And the force, let me do this. It's equal to negative du dx. So it's negative kx. So it's a parabola, and we call this equilibrium here. If you have a mass and you put the mass here, the mass tends to come back here because the force is equal to negative du dx. So it's called the restoring force. So if you put the mass here, it tends to come back. Meaning, if I stretch the spring wants to bring me back to the equilibrium. If I go to the other side, the spring will push me back to the equilibrium. So that's called a stable equilibrium. On the other hand, you could have an unstable equilibrium. For example, let's say I have something that's not a spring and maybe it looks like something like that. If I have my mass here at this starting point, then if I disturb it this way or this way, then it will just go away and doesn't come back to this point. That's called an unstable equilibrium. The way you figure whether it's stable or unstable is if, remember how you know if it's concave up, then it will be stable. If it's concave down, it's unstable. So concavity, if you take the second derivative, if the second derivative of u with respect to x is greater than 0, then it is stable. The equilibrium is stable. If the second derivative of u with respect to x is less than 0, then you have, meaning it's here, it's a maximum, then it will be unstable. That equilibrium, unstable. It's an unstable equilibrium. Okay. So I would like to show you an example of how you can use force or you can use energy to solve a particular problem. So let me erase this, get it out of the way, and then I will put it back. So let's say we have a spring here. Here's the spring. And the spring is naturally up to this length here. Let me call it, let me just look at the book, what they call it. I think they call it L0, yeah. L0. L0, all right? L0. I come along, that's the natural length of the spring. I come along, and then I place a mass on this spring. So here's the original length. So I will place a mass. So slowly I will compress the spring, and the spring will end up here at y equilibrium. At y equilibrium. So how far did the spring compress? Well, it has compressed by this much. By that much. It has compressed by this much, which is L0 minus y at this equilibrium point here. Y at equilibrium. So how much potential energy is stored in the spring? Well, the potential energy in the spring will equal to the 1/2 kx squared. Then x is the compression or the stretch. and we have compressed it by this much, so it's 1/2 of L0 minus Y equilibrium. That's the potential energy stored in the spring, USP maybe, I should say. Now, how about the potential due to gravity? Potential energy due to gravity just depends on how high the mass is. So let's say this is the 0 and this is height y. I would just call it mgy. The potential energy in gravity is just mgy, whatever y is, okay? Whatever, 1/2 kx squared. Yeah, 1/2 kx squared. Let me just, 1/2 kx squared. And let's say, this is y equilibrium. It's a pain. Let me just call it y here instead of keep calling. So here is the y-axis. Here's the y-axis. So the initial position of the spring is L0. That's the height. When you compress it, it's at y, and then this one y, and this one y, and the gravity is also mgy. Depends on how high you're on the spring. Okay, sounds good. So the total potential energy will be the potential energy stored in the spring plus the potential energy due to gravity, and that will be 1/2 k L0 minus y squared plus mgy. So what's the force on this mass? Remember what force was. Force was minus du dy in this case. If we had x, vertically it's du dy, horizontally would be du dx, du dy. And remember, if you have a function of two variables, you have that gradient thing where it's like a derivative in two dimensions. But here, let's just have one dimension. So it's just the derivative with respect to this dimension, the y. So let's take the derivative here. Take derivative, so you get derivative of this, you get the 2 comes down, so and it multiplies this, so you just get k, and then L0 minus y. And then you have to take the derivative of the inside function. Derivative of this is just -1, because derivative of L0, that's a constant, and then minus y. And then derivative of this with respect to y is just mg. And if I ask you, if this mass here is sitting in equilibrium, then the net force on this mass is equal to 0. So where is that equilibrium? So if the net force is 0, then this force, we have to set this to equal to 0. Let's set it equal to 0. So we will have this k, and then L minus y, L0 minus y. And I made a mistake here. The derivative of this is not -y, it's -1. -1 times -1 plus mg is equal to 0. And we solve for y for which this happens. So if you solve for y, take this to the other side so the minus sign goes away, and then you will get y will equal to what? It will be L minus mg over k. That's where it will be in equilibrium. Okay. Let me just make sure I have it correct. L0 mg minus, okay. L0. So you could solve the problem using potential energy. On the other hand, you could solve it not using potential energy, because we could just say the net force on the object is equal to 0 because it's in equilibrium. The net force is, you got an mg downward, and then the force of the spring upward. And the force of the spring is equal to k times the amount by which you have compressed the spring, which is L0 minus y. And you set these two things equal. So you get mg equal to k times L0 minus y. mg equals to k L0 minus y. And you can solve it that way. So they're trying to just introduce you to what's coming. If you take upper level physics, basically there is a new way to do mechanics, not using Newton's law. It's called basically like Lagrangian and Hamiltonian mechanics. You can use Google to Google Lagrange and Hamilton, different ways to formulate mechanics. So there are alternative ways that don't refer to the force, simply talk about energy. Okay? And they're more powerful. They're equivalent to Newton's laws, but they're just more powerful in many ways. Before I end this segment, let me consider this function here, this potential. Suppose the potential energy of an object is this. And the question is, first, what's the force on the object? Well, the force on the object is negative du dx. So you take the derivative of this, so and then put a minus sign. So this is negative 6x squared, and then you have a minus sign here that takes care of this, and it becomes a plus. And then I have you get 6x. That's the force. Let me draw this potential. It looks like here is x, here is u of x, and let's see. So to find the maximum and minimum, I have to set x equal to 0. Remember, if you have a function f of x, to find the maximum or minimum, the critical points, you take the derivative of the function and set it equal to 0. So let's set this equal to 0. So first of all, we found f. When is f equal to 0? F is equal to 0. We have, when we set this is equal to 0, so you get negative 6x squared plus 6x is equal to 0. Divide by 6 and multiply by negative 1, so you get x squared minus x equals to 0. So that means x times x minus 1 is equal to 0. So it's like x equal to 0 and x equal to 1. Those are the critical points. You get a maximum and a minimum. So you have here 0 and 1. X equal to 1. So what is the function at 0? U of 0 is 0. Okay. And then u of 1 will be 2 times 1 cubed is 2 minus 3. So that's minus 1. So you have minus 1. So here the function is minus. If you go to negative infinity, this is negative infinity because this is odd. So it just decreases. And then when, yeah, okay, so it looks basically like this. This is the function. And let's just confirm that. They say, is this a stable equilibrium? And is this a stable equilibrium? Well, at 0, the function, it looks like this. So it's an unstable equilibrium. Imagine you put like a little mass here. If you disturb it to the right, to the left, or to the right, the mass either falls all the way here or it just falls here. However, if you put a little bead, I always imagine like you have a little bowl and you put a bead on it. If the bowl is like this, then the bead will just keep going back and forth. But if the bowl looks like this and you place a bead here very carefully, okay, it might balance, but then you disturb it very little to the right or to the left and it just falls off. So this is stable, this is unstable. So let's just confirm that this is stable and this is unstable. So we take the second derivative of u. So du dx is 6x squared minus 6x, and du dx, the second derivative of du dx would be 12x minus 6. 12x minus 6. So du, the second derivative of u with respect to x when x is equal to 0 will give me what? Negative 6, which is less than 0, so unstable. And du dx at x equal to 1 will give me 12 minus 6, which is positive 6, which is greater than 0, so that is stable. So when x is 1, you get stable equilibrium, and when x is negative 0, you get unstable equilibrium. And I would like to pause this and come back and do, I think, one more problem.